And hopefully we are all good to go. Oh, look, it says chapter 25 at the top. That's old because our old book, before we updated to the new edition last year, all the chapters were off by one. So that's really chapter 24. Used to be chapter 25, but now it's chapter 24. Okay, so chapter 24 is still inference for means. Inference means confidence intervals and significance tests. And we're still doing means, but the caveat on chapter 24 is, well, what if we have two samples, but they are obtained by pairing? So that means we either have like a matched pairs experiment, where you have the same person doing the experiment twice with two different treatments, or maybe you pair people up in your experiment so that two people that are similar to each other are paired. So this says right here, paired is two samples that are not independent and they are matched together. For example, if we were doing some type of experiment or study on married couples, the husband and the wife are not independent of each other. They probably have a lot of things in common, hence the fact that they decided to get married. So those would not be independent. So any opinions or anything about them, we could not treat them as independent. Pre-test, post-test. If you take a pre-test on a topic and then you are instructed on that topic and then you take a post-test, those scores are related because it's the same person. Okay, if the person is someone who had some knowledge ahead of time, these two are going to be connected versus someone who had no knowledge ahead of time. So those are not independent. So someone's pre-test score is not independent of their post-test score. Example, strength of your right versus left hand. If it's on the same person, one person is either super strong and we would expect both hands to be strong. Maybe the right hand is a little stronger than the left is what we would actually be interested in testing. However, they would have a relationship between their two hands compared to a separate person that might not be as strong. So these are all examples of samples that are not independent that are paired. But it's easy. All you do when your samples are paired is you find the difference between each pair of data. We call this a paired t-interval, but all it really is a one sample t-interval on those differences. So we take all the differences and then we do exactly what we did with one sample. So you find the difference for each pair of data and then you treat it as one sample. So you've defined your parameter. There's our P, and we're doing our panic here. So here's our P, and our parameter will be the population mean difference between, whatever. So you can call it like that, mean difference. I mean, you can call it whatever you want, but that's a common way to call it, mu sub d, mean difference. So the difference in heights between a husband and wife, for example, or the difference in strength between someone's right hand and left hand, or the difference between someone's post-test score and pre-test score. Okay, we next check our conditions. So we still need independence and we need random or unbiased differences. So the data is paired, so we're not expecting independence between the values, but we're expecting independence between the people. So we do that by checking, 10% of our population. Our sample needs to be large enough, same as what we've done before. If your sample is 30 or greater, it's large enough. If your sample is less than 30, we need to investigate more by looking at some kind of graph to see if we have symmetry and no outliers to give us some evidence that this might have come from an approximately normal distribution. Next, you name your test. What test or interval? Sorry, this is an interval. What interval are we going to do? We're going to do a paired t-interval. You can also call it a one sample t-interval for the differences, or a one sample t-interval for pairs, or something like that. Degrees of freedom. Your degrees of freedom is number of differences minus 1. So you're going to do a one sample t interval on the differences. Degrees of freedom down here are n minus 1, number of differences minus 1. And then notice this is exactly the same formula that we used before. So x bar sub d is the sample mean of the differences. T star comes from a table. This is the standard deviation of the differences from the sample, and n is the size of the sample. And then you create your interval right here, and then you interpret it in context. I am 95% confident that the interval between A and B captures the true mean difference in heights between husbands and wives, or whatever it happens to be. Okay, we can also do a test in the exact same way. We can call it a paired t-test or a one sample t-test on the differences. Well, what do? We find the difference between each pair of data. Same thing. Phantoms. Define your parameter. You can call it mu sub d. You write hypotheses using whatever you decided to call it over here in your hypotheses. The null will always be that the mean of the differences is 0, because that's saying that there's no difference. So the mean of the differences is 0 versus the alternative that there's a positive difference, negative difference, or just a difference. Step 3. Assumptions and conditions, same as above. Step 4, name your test or provide the formula. So you can call it a paired t-test. You can call it a one sample t-test using the differences. This is all the formulas for where the test statistic comes from. If you use your calculator, you don't have to provide the formulas, but this is where they would come from. However, you do need to give a test statistic and p-value. So there's my test statistic and p-value. You need to observe, is your p-value greater than 0.05 or less than 0.05 or whatever significance level you are using. You need to make a decision and state a conclusion in context. And that's the same as what we've always done, okay? So it's really not that different. A study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown in the table below. A lower score indicates less pain. The before value is matched to an after value. Are the sensory measurements on average lower after hypnotism? Test at a 5% significance level. So we want to see whether the hypnosis treatment that these subjects went through, there are, what, 10 of them? Maybe 1, 2, 3, 4, 5, 6, 7, 8 of them. So these 8 subjects went through a hypnosis treatment. They measured their level of pain before the hypnosis, and then they measured their level of pain after the hypnosis, okay? And what we're testing is, did the hypnosis on average lower their pain? So the sensory measurements, the pain measurements, did they get lowered after the hypnosis? So there are 2 samples here, but do you see why they are paired? Like, in other words, this number is not independent of that one. It's the same person. So the baseline level of their pain before the treatment needs to be taken into consideration. Like, we wouldn't just want to find the mean of all of these and then the mean of all of those, because what if you've got people in here that have a higher level of pain than others? It's much better to pair them. So in other words, these 2 values get paired together. These 2 values are paired together. And what we're looking for is an average, decrease in the pain level across the board. So first thing that we need to do when we figure out that it's paired is we need to find the difference. You can find the difference in either order. So you can do before minus after or after minus before. It does not matter. I'm going to do after minus before, but it does not matter. It just will change the inequality sign that you use in the hypothesis that you're using. So we're just going to subtract all these. So if I do 6.8 minus 6.6, this is a difference of 0.2. So interestingly enough, this subject actually had increased pain after they went through the hypnosis. The second person saw a decrease. Negative values would represent a decrease, which is really what we're looking for. We're looking for decreased values here. The third person also saw a decrease, negative 1.6. The next person, 8.5 minus 10.3 is negative 1.8. 8.1 minus 11.3, negative 3.2. 6.1 minus 8.1, and I don't know why I stuck that in the calculator. I did not look. Minus 6.3. Negative 2.9. And then 2 minus 11.6. This last person, major decrease in their pain level. Okay. Now, once we have done this, you can ignore all of that because now we're just looking at one sample. So we're going to do everything that we have done before with one sample, but we're going to use these differences. Okay. So first thing we need to do is define our parameter. So I'll call it mu sub d equal the mean of the difference in pain score is what I'll call it. Pain score, and we can even say it's after minus before. With hypnosis. Okay, so that's what we're looking at, the mean of the difference. Okay. By the way, mean of the difference, okay, that's what this is. This is the mean of the differences. This, what we have seen before, that is a difference of the means. You guys see the distinction there? So this is the difference between two means. This is the mean of a bunch of differences. Okay, so just be careful on how you say that. Oh, I didn't even, yeah, there we go. So just be careful how you say that. So this is the mean of the differences. Okay, our null hypothesis. There's not a lot of room here, I just noticed. So our null hypothesis is that the mean difference is 0. In other words, the hypnosis does nothing. The alternative is what we are hoping to prove, or I guess the people doing this treatment is hoping that they can prove, in that the hypnosis will lower your pain score. So we would want a negative difference. All those negative differences represent somebody who had a lower level of pain after they went through the hypnosis. Okay, our conditions. I'm going to do conditions over here on the side because there's not a lot of room there. Okay, so conditions. Okay, so the first thing is we need a random sample. And it does say that these were randomly selected subjects. So we can say for randomization, subjects selected randomly. 10% condition. Okay, if we count, we got 9, 8, 1, 2, 3, 4, 5, 6, 7, 8. We got 8 people here in this study. So n equals 8 is less than 10% of people that have pain and could receive hypnosis. I mean, that's really who our population is. hypnosis. Our population is all people who could, in theory, be treated by hypnosis. So those are people that, experience pain and could, in theory, be treated by hypnosis. So I don't know what that is, but I'm sure that there's much more than 80 people who experience pain on any kind of regular basis and could, in theory, be treated with hypnosis. Okay, large sample. This is where we have a problem. N is 8, which is less than 30. So I need some evidence to see that these are relatively symmetric. And I'm going to put them in my calculator. So stat edit list 1. Fortunately, there's only 8 values here. 0.2, negative 4.1, negative 1.6, negative 1.8, negative 3.2, 2. Okay, so I got all 8 values in a list. I'm going to go to my stat plot, turn it on, use list 1. I'll go ahead and choose my normal probability plot since that's what's already selected. Zoom 9, there's my normal probability plot. I do see this one outlier over here that is perhaps concerning. If I go to my histogram, we will most likely see that outlier there as well. It's relatively symmetric, possible outlier. So I'm going to at least mention that. Because on both of those, I could see that outlier right there. But other than that, it looked pretty symmetric. Okay, so histogram is reasonably symmetric. An outlier. And I'm even going to do a box plot. And the box plot will confirm whether it is considered an outlier. So if I do the box plot that shows little outliers right there. Yep. An outlier is a concern. We will proceed with caution. Okay, so in other words, I don't know for sure if that really is an outlier. We only have a sample of size 8. If we had a larger sample, maybe all of these values here would be filled in. So maybe it's not so much an outlier in the sample it is. Is it an outlier in the population? I don't know. So proceed with caution means, if that truly is an outlier, that's going to affect our results. But if it's not, and if we had more subjects and all of that stuff got filled in, it's not really an outlier at that point. So at the very least, I do have some concerns about that. But we will go ahead with a 1 sample t-test on the differences. You could also call it a paired t-test. Okay, so 1 sample t-test is just your regular 1 sample t-test. Right there, number 2, t-test. Options. Is the data in the calculator or do you have to enter in all the stats by hand? The data is in my calculator, and if you were doing this on a test, the data would be in your calculator. So my null hypothesis is 0. My data is in list 1, and I am doing a less than test. Look at my alternative, says less than right there, so I choose less than, hit calculate, and I've got, oh, I forgot my degrees of freedom is equal to 7, 8 minus 1, x, or just writing everything on the screen here. T is equal to negative 3.04, My p-value is 0.0095. There's my p-value right there. X bar, that's the mean from the sample. So it doesn't hurt to include that. So in other words, our point estimate of the reduction in pain, we're estimating on average a reduction of pain of negative 3.125, because that's our point estimate, with a standard deviation of 2.91. But of course, the important part of this, even though we got it reported all, that's the important part. Our p-value, is it less than 5%? Because it says to test at 5%. So right up there, 5%. Is that less than 5%? Yeah, definitely. Okay, since the p-value equals 0.0095, which is less than 0.05 by quite a lot. I mean, it's not even just a little bit less, it's a lot less. Okay, when you have a small p-value, I reject the null hypothesis. Okay, in rejecting the null hypothesis, we are saying that it appears we have convincing evidence that the sensory measurements on average are lower after hypnotism. Okay, so there is convincing evidence that, and what is it called again? Sensory measurements. That's pain measurements. But if in doubt, use the wording from the problem, are lower on average. I'm literally just writing everything from the question there. Average after hypnotism. Okay, that's literally what it asks right there. Are the sensory measurements on average lower after hypnotism? So we're saying that we have convincing evidence that that is the case. Okay, remember, we never prove anything, so we never know if that's absolutely a fact, but that's what the evidence leads us to believe. So we have convincing evidence that that is true. Okay. It says create and interpret a 90% confidence interval to estimate the reduction in pain after hypnosis. Nice thing is we've done most of the work here. We've defined our parameter. We've checked our conditions. Don't need to do that again. So we can go straight naming our 90% confidence interval. So we're going to do a 1 sample t interval. Interval on the differences. And that's going to give me my confidence interval. So stat, test, t interval. Make sure you never choose a z interval. We do a t interval. The data is in my calculator, list 1. I am doing a 90% confidence interval and calculate. And my confidence interval is negative 5.075, comma, negative 1.175. Okay. Now notice that a 90% confidence interval is the same significance as 5% significance. So that's why it actually says to do a 90% confidence interval. Just as a reminder, when you do a 90% confidence interval and we do a less than hypothesis test, this is our alpha level down here, which is 5%. So in other words, this confidence interval should give us the exact same results as the test, which is, hey, look, all the values are negative. That confirms what we said up here. We do have convincing evidence that hypnotism is going to lower the pain score as much as 5 points, but it could be as little as 1.1 points. Okay, so if we interpret this, I am 90% confident that the interval from negative 5.075 to negative 1.175 captures the true mean difference in pain score and this is after hypnosis minus before hypnosis. Yeah, so since it's all negative, there's evidence, or we are confident that there is a reduction in pain score. However, even though it's significant, and it's very significant, I mean, this is a very, very low p-value, it is possible that the reduction is not practically significant, which means, is it worth spending money on hypnosis treatments if we might only end up with a 1-point reduction? Who knows? We estimate that it's probably around 3 because that's our point estimate, but our confidence interval says it could be anywhere between a 5-point reduction, to just a 1.1 point reduction. And of course, that's not our call, but that is something for the people involved in the experiment to take into consideration. Okay, next, can a food additive increase egg production? Agriculture researchers want to design an experiment to find out. They have 100 hens available. They have 2 kinds of feed, regular feed and new feed with the additive. They plan to run their experiment for a month, recording the number of eggs that each hen produces. Side note, when I was in college, I actually had a job with a poultry expert, and we ran experiments like this. I did the statistics for them. This just reminds me of that. That was a long time ago, but it was very interesting. Okay, so design an experiment that will require a 2-sample T procedure. Okay, for a 2-sample T, how many samples do we need? 2. We need 2 independent samples. So what do we have to do with these 100 hens? Yeah, we got to separate them into 2 separate samples. So the experiment here would be doing an experiment where we separate our hens randomly into 2 groups, 50 and 50. One group gets the regular feed. The other group of 50 gets the new feed with the additive. And then they receive those feeds for the month. And at the end of the month, you compare the number of eggs, from each group. So the average number of eggs that each hen has been producing. Okay, so that's how the experiment would run if we were interested in doing a 2-sample T procedure. So we would do a, so randomly assign hens to 2 treatment groups. Okay, so you can do that with a random number generator. You can give each hen a number from 1 to 100, and then using a random number generator, pull 50 unique numbers. They go into the first group, and then the other 50 hens go into the second group. So if it asks you, how would you randomly do it? That's what I would do. I would number these 1 through 100 and use a random number generator without repeats to find 50 unique numbers. Those 50 hens go to group 1 and the other goes to group 2. Okay, so one group is given regular feed the other, the new feed. Okay, and this is, for a month. And then at the end of the month, what we're interested is, the number of eggs that are produced by the two different groups. So compare the number of eggs, which really we would be looking at the mean number, for each group. Okay. If we did that, we would be doing a 2-sample t-test. So we take the number of eggs from group 1, divide that by 50 because there's 50 hens. Take the number of eggs from group 2, divide that by 50 because they had 50 hens, and then you do a 2-sample t-test or 2-sample t-interval using the two groups. Okay, same scenario, but what if instead of a 2-sample t procedure, we wanted to do a matched pairs t procedure? So how do we set this up differently? So here we don't want 2 independent samples. We want 1 big sample. And what do? So how do we make this matched pairs? 100 hens, what do we do with them? Yeah, Catherine? There you go. So you feed all the hens the regular feed for part of the month, and then you feed them the other feed for the other part of the month. So each hen gets both types of treatments. Now we still need to have some randomization in here, so we can randomly decide, like with a coin flip, whether they get the regular feed for the first part of the month or the additive for the first part of the month, but they're going to get both of them. So each hen receives regular feed for 2 weeks, because we want to do this for a month, and the new feed for 2 weeks. So that'll take care of our month. Use a coin flip. Or any other kind of randomization procedure, but we got to decide, are you going to get the regular feed first or the new feed first? Use a coin flip to decide which treatment is given to each hen first. So you got hen number 1, you flip a coin. If it's heads, you give them the regular feed first, and if it's tails, you give them the additive first. So you do that for each hen. And then at the end, for each hen, we would calculate the difference in the number of eggs between the 2 treatments. Okay, so then we would, after the month, calculate the difference in the amount of eggs for each hen with the 2 feeds. Okay, so we don't have 2 samples anymore. We put them all together as 1 big sample, They each get the 2 different feeds. And then at the end of the month, we just take the difference for each hen, which is back to what we just did right here. You take the difference for each subject. So each hen has a difference, you know, regular feed minus new feed or whatever, doesn't matter the order here, but you take the difference. And then you use a matched pairs or a 1 sample T procedure using those differences. Okay, last question. Which one do you think has a stronger design? So which one do you think would be better? Remembering that with an experiment, what we want to do is control outside confounding factors as much as we can. So which one do you think does a better job of that? So here we're comparing 50 hens with a different set of 50 hens, you know, with the 2 different treatments. Here we are comparing each hen with herself. Which one is going to control outside factors of variability better? Yeah, second one. Because what if, I know it's random, but what if up here you end up with, you know, out of these 100 hens, you've got a few super layers and they end up all together in one group with the new feed. So that group ends up with a much larger mean than the other group, but maybe it's really not due to the new feed. It was just that, hey, random chance. You ended up with some really super laying hens in that group, and the other group had hens that don't lay as much. Here we control for that because each hen is compared to herself. If she lays a lot of eggs and the new feed doesn't do anything, she's going to lay a lot of eggs regardless on both feeds. If the new feed really is significantly better, then we would on average expect that each hen is going to lay more on the new feed compared to the old one. Okay, so which one is better? Matched pairs. Matched pairs allows us to compare each hen against itself. This helps control confounding factors such as laying ability. There might be other confounding factors, I don't know, but that's one that I can think of. If you have out of your 100 hens a whole bunch of different laying abilities, we do want to make sure that that is not part of our experiment. Okay, and this last page, this is just a flow chart. You guys have seen flow charts before, but we now have proportions and means. So it is important that you can tell which one is which. Now, when we do our test next week, like our literal test, not like a significance test, but when we do our literal test, yeah, it's going to be chapters or unit 6 and 7. So it's going to have means on it. It's not going to have proportions. However, when you take the AP exam, it's going to be all mixed. They're not going to say, hey, here's a problem dealing with proportions. Hey, here's a problem dealing with means. You got to be able to tell the difference. So first question, when you know that you're doing an inference problem, inference means confidence interval or test. Test meaning that they ask you for convincing evidence or is there evidence. So if you decide, oh, this is an inference problem, they want me to do a confidence interval or they want me to run a test. First question, is the data given to you as a percentage, a proportion, or some number out of some other number? So if they say, you know, there are 10 people out of 50 that believe this, those are the indicators that this is looking like proportions. So if that is the case, okay, you say yes. Next question, how many samples do you have? If you have 1, then we're going to do a 1 proportion Z interval or a 1 proportion Z test. If you decide that there are 2 independent samples with proportions, you're going to do a 2 proportion Z interval or a 2 proportion Z test. Remember, proportions use Z. Okay? Because we don't have to put the S into our formula. It's whenever we use S in the formula, when we don't know sigma, that our normal model turns into a T model. That doesn't happen with proportions. Okay, if you decide it's not proportions, double check. Does the problem involve means or averages? So if you're reading the problem and it talks about the mean or the average, or, data is given as another indicator here. So you're given a list of data, kind of like we had with the hypnosis, a list that you would actually put into your calculator. So if you're given a list of data that could be put into a calculator, yeah, that's an indicator that this is probably means. Next question, how many samples? If you got 1, you do a 1 sample T interval or test. And again, since this is means, it's T. If you say there are 2 samples, then the next question is, are the samples independent or are they paired? Okay, so if they are independent samples, you do a 2 sample T interval or test. If the 2 samples are paired, then you take the differences and you do a paired T interval or test. And remember, that is on the differences. So when you do this, you actually subtract them all, and you're really doing a 1 sample T interval or test. You're just doing it on the differences. So a paired T interval or a paired T test is a 1 sample T test or interval on the differences. So in other words, you're taking 2 samples, combining them by subtracting into 1 sample. So you make them 1 sample versus 2 completely independent samples. Okay, so that is chapter 24. And we've got this time, see, we got more time this time. So we have 25 minutes. And there was a question on the last assignment. I just need to find it on my email here somewhere. And we can go over that. Oh, and then group A, we didn't get to talk about the last Frappy, so I will do that at the end of the period. Group B was able to do that on Friday, but group A did not, so we will do that with group A. And I don't know how to spell instructor. Instructor. Okay. Okay, so your only assignment, like I said, is, I'll pause